Uh, Hello, good morning. We are Team Krish AI. With me, we have Kavin Ramesh from IILM University, from VIT Vellore, and myself, Nihal Puram, from IIT Madras. We are here to give a small overview of our project for the Alibaba Hackathon Innovation Challenge. All right. To start off, we have Kavin Ramesh, who's going to talk about the problem that we chose for this challenge. So yeah, Kavin.
Yeah, change the slide, Nihal. Right. So obviously we need to get into why we chose the problem and what the problem is, and very easily put, it is the problem of water scarcity. Inefficient water usage throughout the centuries and millennia has caused a lot of water scarcity coming to this day. You'll find loads of statistics that details as to how bad we are in this situation. If you look into the World Bank, we can talk about how significant this issue is when it comes to agriculture, that accounts for, on average, 70% of all freshwater withdrawals globally. Uh, there is an Indian think tank that we have here in India, and that's called the Niti Aayog. And the Niti Aayog itself has declared, or has at least stated time and time again, that many urban areas within India are at risk of completely running out of groundwater. In fact, one of the biggest examples you could find was in Chennai back in, I think, 2019 and 2018, where they faced severe groundwater shortage to the point where people had to wait in lines for hours and hours on end just to get a bucket of water. This is the kind of issues that we are facing today, and we will continue to face them tomorrow and the day after. These are the sort of issues that we need to take very seriously, because at the rate at which we're consuming water, can only get worse. Which is why we decided that if we're going to use technology, let's try and apply it to a solution here. Next slide, Nihal.
Yeah.
Yeah. So just to show you what actually happened, we need to look at the per capita water supply. This is one of the most important statistics when we talk about how we use water as a population. Now, as you can see here, there clearly was a huge, a huge diverge when it comes to the per capita water supply and the population. Because back then we were a very water sufficient country, but as time went on, we now are one of the worst hit water deficit countries. And because we see that there is a clear diverge between our population, as in due to our high growth, as well as the water that is available to meet our demands. In fact, the Niti Aayog had even said that by 2050, aggregate supply of water will not be able to meet the aggregate demand of the Indian population. And this is not just an Indian problem. This is global. We as Indian citizens, I think all our teammates are Indian citizens here, and we thought, why not look into the ground level of what India is facing at the moment? Next slide, Nihal.
Right. Yeah.
As I said earlier, agriculture requires about 70% of water as per the World Bank. And when you think about why that is, this slide just tells you all it needs to. So there's this concept called virtual water, which is essentially the kind of water you require to ensure the yield of this stays consistent and good. And as you can see, different crops require different amounts of virtual water, and there are an insane amount of virtual water for just very small units. Look at, for example, beef, which takes about 4,650 liters for just a few units that you might find in a restaurant or you might find in a big hotel. And just imagine, this is not one hotel we are talking about. We are talking about an entire global supply. So again, not an Indian problem, but rather a problem that every country in the world is going to face either today, or they faced it yesterday, or they're going to face it tomorrow. A lot of countries already face these issues, including India, and sooner or later it will impact the more developed countries.
Yes.
Next slide, yeah. So, why should we solve this problem? So, I spoke about what is the problem, I spoke about why we chose it. What happens when we do solve it somehow, by hook or crook? Well, if we can come up with a solution to solve this kind of problem. It works in the public space, it works in the private space, especially when it comes to agriculture. Now, in agriculture, as we all know, there are small farmers, there are medium farmers, and of course, there are large farmers. In India, there is a huge population, I mean, majority of the population are small farmers, but there are huge industrial farmers all across the country, from Telangana all the way to Punjab. So, when you come up with a solution that we'll talk about soon, you could actually involve not only the government, but also the large scale agricultural farmers and the small farmers. Because the costs involved in this project initially are going to be high, so you would want the large scale farmers who can afford it, as well as the government who can subsidize it for the small scale farmers. This direct resolution can actually solve a lot of mass wastage that we see in the public and private sector. And
Yeah.
this is something that is already being invested into by a lot of governments, by a lot of corporations. This is not something that we have chosen out of the blue. Our government, and as well as the state government and the corporations, are already looking for solutions. Have they come across certain optimizations? Yes, but they haven't really solved the problem as such, which is where we are trying to come in based on how we're going to really effectively optimize the way water usage is done. Next slide.
Yeah. Coming to the solution or the idea that we have, uh, so this is a very radical and a very different idea that we have. So traditionally, we used to have systems where farmers would get, once in a year update of what their soil might look like, or sometimes even there is no update for a couple of seasons. So what we want to do is to bridge the gap between farmers and the science. And how we're doing that? So we're doing that using AI as a forefront technology, along with IoT as a complete infrastructure behind it. So basically, we will be using AI trained systems to be assisting farmers uh, to grow crops. So we'll be using AI systems to assist farmers. Um, in the long run, what we aim to do is to use our resources efficiently. These resources might include water, this includes minerals, this includes nutrients, micronutrients in the soil. We'll be having to optimize for rainfall. This also might lead to more study into water irrigation systems like canals, etc. So overall, in the long term, this project aims to make all of these systems around farming more efficient and indirectly help the farmers or the farming system in India or as a global process more efficient. So, so that's the basics idea of what we have. Now, how are we going to do that? So for this, instead of the current, weather advisory system, we are having a post-harvest feedback loop. So basically, we will be directly involving with each farmer as in an individual basis and having a feedback loop where uh, the current parameters are set, and based on the reactions to that, we can try and change the parameters in such a way that we will be improving the model or improving the crop yields year by year by year. So, as a phase one of this idea, we're talking about rainfall, and this is going to be the major part of our project for this hackathon and what we are doing as a team. So, the idea is basically countries, especially the tropical region like India, experience a lot of rainfall every year, and a large part of this rainfall is used for agriculture. But on a more practical sense, a lot of the farmlands in India or in tropical regions still rely on groundwater-based pumps for irrigation, and this leads to a lot of water wastage, and undoubtedly, it also is not sustainable. So although it is very good for the farmer in the short term, but going into the future in a couple of years, maybe 5 or 6 years, when the groundwater starts to dry up, we are going to see a lot of food scarcity, and it's a huge food security problem for the people of the region. So efficient water usage is one of the most critical points that we're trying to address. So for this, we will be making a state-of-the-art model using a lot of techniques which we'll be talking about later in this video and in the presentation. And through this, we will be trying to predict the amount of the rainfall or the weather conditions in the future, and how suitable it is for the growth of the plant. And based on that, what kind of things that we need to supplement the plant on a day-to-day basis. And this is really important, as when we give information on a day-to-day basis, this provides the farmer an option on whether to use his resources of his groundwater resources more conservatively, and to prolong its life into the future. So this is for phase one. So for this, we'll be analyzing satellite data, and also we will be looking at radar reflectivity data of certain regions, and we will be making weather nowcasting models combined with traditional weather models, and a couple of other LSTM and transformer network based models. And an ensemble of these models will be using it to predict the exact number of or the amount of rainfall a certain region might experience. So, in a situation where a certain region might experience rainfall in a couple of days or in the immediate future, we would be recommending the farmer to use less amount of groundwater in that time. So, indirectly, we are trying to help him save groundwater for the future and also preserve the sustainability of the groundwater resources of his land. So, this is our phase one project of how we are planning to optimize rainfall or water in specific. So coming to phase two, I have my friend here to explain what we are planning to do in phase two.
So in the phase two, as Nihal has mentioned, in the phase one, we concentrate on the satellite imagery and other patterns, and predict what like plant or what water should be used and how much water should be used. So in this phase two, we plan to make it very localized. That means we are like actually keeping sensors in the farmland and acquiring different kinds of data. In our case, we are like plan to take temperature, soil moisture, and like other various parameters that can help the farmer to utilize the resources very efficiently. So in this we suggest using this model, we suggest the crop pattern rotation, and so that it will also be very economical to the farmer. So in the soil moisture, like especially the soil moisture data or the mineral data that we provide to the farmer might not understand them directly, so we process that data like and tell them what to be done. Suppose if the soil moisture is very much, and the plant does not require that much water in that day, in that particular day, so we can reduce the amount of water given to the crop on that day. And if suppose a particular mineral or some other parameter is very much, and you can reduce that in that area. Also, we plan to include image processing based infection or disease identification of the crop, so that the farmer is well informed about the that particular disease or pest before it reaches. This is all regarding the crop and the utilization of the resources properly, and this also helps the farmer to utilize the water properly, and do not help him dependence decreases dependence over the groundwater very much.
Yeah.
So moving on to the soil health card.
Yeah. So indirectly, like we are trying to ensure food security in the region, and also help the farmers make make growing crops more efficient and better, and get better yields. So now we have a visualized plan for phase one. So step one, we'll be accurately trying to predict the amount of rainfall and analyze rainfall patterns to utilize rainwater more efficiently and decrease our reliance on groundwater resources in more critical regions. Step two, we'll be using AI systems to enable prediction of groundwater levels via satellite imagery of the area. And then third step is we are using computer vision implementation to measure the growth of the plant and to optimize and evaluate water needs along with the crop type and growth phase. This also includes using the sensors, like my friend has mentioned. We'll be talking about the details of what sensors we are using and preliminary idea of the product that we're coming up with. But for now, this is the idea that we have. Um, so using all of these, we'll be able to optimize our water needs, and also we'll be able to optimize our micronutrient and nutrient needs for each type of plant and for each soil specifically. and therefore we'll be reducing the level of need of virtual water. Right. For phase two, we'll be gathering information on the soil, especially the soil moisture, the components of soil, etc. We'll be calling this soil profiling, and based on Government of India's soil health card program, we'll be generating a soil profile card. It's quite similar to what is there now. My friend Kavan will talk about the specifics in a minute. So based on the soil profile card, we'll be suggesting crops that make a fit of the soil based on the various parameters. And we also need to take into consideration the market of the local region, as that also affects the farmers' decision making. And based on that, we'll be looking into the most economical and most sustainable options. And we also do crop rotations based on the soil type of what we gather information from soil profiling. And phase three, this is a vision for the long term. This is what I see or the team sees as a long term future for the project. So number one is we'll be suggesting water rationing using AI to efficiently grow plants in region with moderate or severe water scarcity. And water scarcity is something that some of the regions in the world experience right now, but in the future it is being predicted that a large amount of population will be affected by water scarcity, and growing crops and food security in such times is of high precedence. So I think our model or our system will be able to help with that. And the second vision is to analyze local water bodies like lakes, rivers, canals, etc., and kind of map out water levels and to see whether they're suitable for irrigation and also for usage of variety of industries. So this is not specific for agriculture. This is general water usage for all kinds of industries, and especially right now, the way we do water management in the country, it's not very well regulated. So using our systems, we'll be able to monitor water usage from different industries and also be able to make any changes or to try and optimize them later on. Uh, Third one is to possibly introduce hydroponics to small scale farmers, which can generate useful data. So this is in extreme situations where we will be going into severe water scarcity, and this is also a continuation of what we think will be going into the future. So the last one is, as the global trend of water scarcity increases, we need to ensure food security, which is in line with the mission and objective of the Food Corporation of India. And I think I speak for not only India but for the whole world, as food security is a problem which the whole world is going to face in a reasonably short amount of time. Um, so this I think our problem and our solution can solve that to some extent. And this is a dashboard style monitoring system. So this is just an example image of what we are trying to the information that we're trying to provide to the customer or our client. That is the government or the farmer. So our client being the government and our customer being the farmer. So over here, we'll be providing information such as the current growth rate of the crops, the current state of the soil, the amount of nutrients present there, the ideal amount of nutrients that's supposed to be present there. And we'll be providing information about the amount of water that's expected in the coming hours versus the amount of water that the farmer needs to be, you know, the amount of water that he needs for the crops. And all of this information will help the farmer decide on how to more efficiently use his resources. So at the end of the day, this is what we want to do. We do not want the farmers to be unnecessarily wasting their resources or their money on any sort of fertilizers, etc. So we will be giving accurate information on exactly what needs to be done. Everything will be on a dashboard side style system on their mobile phone, and all of this will be backed up and by our infrastructure on Alibaba Cloud. So, and we'll be talking about that infrastructure also later on in this video and in the PPT. Right. So next, the soil health card scheme. Um, yeah.
I'll take it over from here. So yes, my team and I have repeatedly talked about soil profiling and have often used the term soil health card, SHC. This is basically a scheme started by the government of India, where essentially every 2 to 3 years, based on the soil analysis of how a person's holdings might be, a printed report is given to them as to how their soil is expected to hold for the next few seasons. We are talking about all sorts of nutrients here. We are talking about all sorts of fertilizers that are all involved. Uh, this is a very popular scheme. It was started quite a few years ago. But the idea is that you essentially tell the farmer that this is the state of your soil and these are the sort of crops that you can grow on the soil. This soil may not be suitable for a certain type of crop, but it might be suitable for this crop. So you're essentially recommending based on the health of the soil. And you have various dashboards for that. There is already an established dashboard based on the government of India, but we want to give a simplified one that is not only spontaneous but continuous. We want to cut the waiting time from 2 to 3 years to 1 to 2 seasons. That way, a farmer can effectively adjudicate what their soil is going to look like for the summer, for the winter, for the spring, for the monsoon, regardless. You're talking about quite a few nutrients here, but the idea is you want to talk about N, P, and K, nitrogen, phosphorus, and potassium. The three main ones that you find in almost every large-scale fertilizer that you'll find almost every farmer, small or large, use in their farms. We're also going to talk about micronutrients, and of course, you're talking about the moisture. Mihir had pointed out earlier that there could be a situation where a certain crop may have too much moisture, and that it cannot grow sustainably or on a healthy way. So that way, you're essentially telling the farmer this is how you genuinely need to grow these crops. And if you don't want to grow these crops, here are alternatives for you to try out. You're talking about helping the farmer make a good decision, not only based on their own experience that they have plenty of, but also based on the science of which we are adjudicating the health of the soil. This can help large scale farmers, this can help small scale farmers. The idea being that a large scale farmer can afford this directly for their own lands, and for small scale farmers, we can work directly with the government itself, who would very happily support these initiatives to subsidize for the small scale farmers, which is about 80% of the Indian farming population. So that's hundreds of millions of people that we are helping with this one small addition in our phase 2 plan. Next slide. So yeah, the benefits and the innovation aspects of it. Uh, as we've said before, this is not just aiming at containing or countering water scarcity. It's also about helping the farmers financially and economically. We are talking about efficiency of resources, and at the same time, we are talking about just the helping the environment in general. The idea being that with phase 1 and phase 2, you can not only analyze the region but also localize it to the very soil, based on which you can define what crops would be best for that region or what crops would be best for the farmer at their current financial level. And keep in mind, this is only a preliminary stage. When we talk about scaling up, if with the help of Alibaba or with the government of India, we are talking about a situation where we're not talking about soil management for one farmer. We're talking about soil management, land surveying, and water management across communities. We can talk about state to state, we can talk about Telangana and maybe another state of India helping out each other. We can talk about India and Pakistan helping out each other on surveying the Indus water resources. This is the kind of scope that such a solution might have. And you're talking about helping the environment and at the same time helping the economic aspects of the country. As Nihal said, food security is very important. The global south is currently facing a situation where climate change will effectively render us insecure when it comes to food. So we are not only being efficient with our food security, but we are paving the way for long-term sustainable agriculture based on long-term sustainable water usage. And those are just some of the benefits that this innovation can come up with. Next slide, Nihal.
Factors, but the ecological benefits as well. Yes. Yeah. So we are at the technology implementation part of this project. Joining me, I have Rizwan Khan from IIT Madras. I have Tirumalai Vasan from IIT Madras, and myself, Nihal from IIT Madras. Um we'll be training multiple ML and DL models to perform very specific tasks. So this includes the usage of datasets like the Tianki dataset, the TASRAD 19 radar sequences dataset. Going into the more specifics about this, we'll be talking about in this video and also in the PPT. They will also be using other models, which we'll be talking about too. In our phase two, we'll also be using data from soil moisture sensors and other sensors, etc., to further improve optimization and efficiency and to further along our goals. So, talking about the specific technology and about radar reflectivity, we have Rizwan Khan. So, continue.
To predict the precipitation that's gonna happen in the future, the main traditional methods that are used are mainly numerical methods where you do some radar it's you do some radar extrapolation and you describe some large scale equations based on the evolution based on some initial conditions. These take some really long time because it's computationally heavy. Uh, so we take a deep learning approach where we use convolutional LSTMs to predict the precipitation with radar reflectivity data. To talk about convolutional LSTMs, so about convolutional LSTM model, so conv LSTM is really a LSTM network where the hidden states and cell states are three-dimensional instead of two-dimensional. In a instead of two-dimensional, where hidden states and cell states are computed using convolutions rather than fully connected layers that you use in traditional LSTMs. And precipitation nowcasting is actually a spatio-temporal sequence forecasting problem where spatial as well as temporal sequence come in. To capture both of these sequence, we use convolutions to actually capture the spatial relationship, while we use hidden state and cell states to capture the temporal relationship. This way, we fulfill the spatial temporal sequence. And we used encoder decoder framework where we use convolutional LSTMs, where convolutional LSTM at the start encoder part it encodes the input and the decoder outputs a sequence of predictions. Uh, we trained our convolutional LSTM model on TASRAD 19 dataset, which has data from 2010 to 2019 of about 9 years of data, and we were able to train the model for 3 epochs with our limited computing resource. Um, we were really able to get some remarkable results just for training with 3 epochs. And bro, go to next slide.
Yeah.
So TaskRed dataset is really so each 24 frames in dataset then TaskRed is equivalent to 2 hours. So what we are doing in our network is we are taking 12 frames, which is equivalent to 1 hour, and we are trying to predict the 24th frame, which will be equal to the second hour in the decoder part. So doing this, we got some doing this for 3 epochs. We got some remarkable results uh, using only our limited computing power. Of in the future, uh, with Alibaba's machine learning server, we are planning to train the model for more epochs. That way the results will be are expected to be great. Uh,
Yeah. Just to add on to that,
that's it.
we will be using multiple models trained for multiple time periods, and we'll all be doing this using Alibaba's machine learning framework and their powerful servers with powerful GPUs. All right. Um, so going back to our data set, we are using TASRAD 9 data set, and there's a specific reason why we are using this data set. So I'm going to be explaining to you about that. So yeah. So this is our core data set for our radar reflectivity nowcasting model. So it's a high resolution collected by some civil protection weather radar of the Tyrol region in the Italian Alps. It consists of 9 years of data from 2010 to 19 and over 800, almost 900,000 scans. So it's a very big data set and it's very huge. Each image covers an area of roughly 200 square kilometers. 200 kilometers in length and a diameter of 500 meters in the horizontal direction. And it has curated a sequence of 1700 sequences for a total of 362,000 radar images labeled. Each one is labeled with the precision type tags assigned by expert meteorologists. So using this dataset, we will be using the convolutional STM on this dataset, and let's see what kind of results that we are getting. So um, for our final model, we will be using an ensemble of multiple models, which includes our self-trained TASRAD 9 radar reflectivity-based conv LSTM model, which will be used for the short-term nowcasting, which is more relevant to what we are trying to achieve for our specific purpose. And we'll also be using other models like an encoder-decoder attention-based transformer, which will be trained on time series rainfall data, a MetNet trained on satellite images and precipitation rates, and also we'll also be using some part of traditional weather forecasting data. The idea of using an ensemble is that our predictions vary with different lengths of time, and each model is effective at certain predicting at a certain time in the future. TASRAD 9 or radar reflectivity based weather nowcasting is not very good at predicting very far into the future. It's quite good and quite efficient at short term predictions for a few hours, but more than that, it's not very useful. So using an ensemble, it allows us to have accurate predictions across all time frames. Where when we are trying to predict short term, the TASRAD 19 will take precedence, and when we are going for a more long term or more distant forecast, the other models which are relevant will take precedence over our TASRAD 19 model. So this allows us to have accurate predictions over across all time frames. So yeah, Tirumale, you want to continue with the next slide?
Yeah. So these are our next future which are models which will be there in the ensemble. The first one is a encoder and decoder based attention based transformers. This model it will be trained on the time series rainfall data to predict what will be the future rainfalls data. Rainfall will be occurring in the future like that. So this is how the diagram of that model. And next we will be using the state-of-the-art model named MetNet, which uses satellite images of the Earth, and also the precipitation rates, which is also given in the forms of image to predict the future rainfall at each place as a image. Yeah, next.
So to
This
conclude,
Rizwan is going to explain.
yeah, we'll just give conclusion after this. Okay. Yeah. So to conclude, I think our we need a lot more computational power, and we hope Alibaba can provide us that computational power to train all of these models. But looking at the limited data that we were able to train and the limited number of epochs, I think our model is very promising. Yeah, so to conclude, you can check out our code. It's completely functional. We have the GitHub repo link in the PPT. You can try and run it and see. But yeah, to complete the training, we probably need access to a high performance GPU or a machine learning server from Alibaba. And we are hoping that Alibaba can provide us the same. So yeah, to continue. So now we have the hardware implementation, especially in phase 2. And Mihir is going to talk about this.
Okay, for the hardware, as I mentioned, the requirements for the hardware, there are various requirements. First thing is we need a camera to constantly monitor the growth of the crop or any disease or a pest is growing in the crop to monitor those. And we need in the phase 2 we need a soil moisture sensor and other localized parameters such as temperature, humidity, and air pressure that is available in that particular area. And obviously for this data to go from the point which is very far away to be sent to the station where it has network availability, and finally to the database where it can be processed in more efficient way, and a microcontroller to calculate few smaller things and send this data to the uh, local server or the global server. So in this we plan upon using TM32F401, which is a microcontroller it uses ARM Cortex M4 and it has a clock speed of 84 megahertz. And the added advantage with this particular microcontroller is it comes with a DSP extension. That means in some cases, if the network is not proper, it can provide some localized calculations and provide the data to the farmer if required. And the second component is OB2640, which is a 2 megapixel camera, which provides an array size of 1600 by 1200 uh, 1200 elements. So like this camera used for crop growth and all, as I mentioned. And this data from this images, or the camera images, that is sent to the server so that it can be processed, and the crop growth can be rate of crop growth can be identified, or the pest. And for the next component that we plan upon using is the Seed Studio Groove Soil Moisture. It is a soil moisture sensor that identifies the moisture content in the soil. It is a capacitive sensor, so it must be going into the soil, and should be having giving an analog output depending on the voltage between the capacitive ends of the soil moisture sensor. And also in the STM32F401, there is a 12-bit analog to digital converter available. So the precision of the soil moisture that can be uh, 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 noted down is very high, as it is a 12-bit ADC. And the next component is BME 280, which is a temperature, humidity, and a pressure sensor from Bosch. So with this component, we are using it here to identify the temperature and the humid conditions in a very localized way, in particular to that field. There might be some situations where the local temperature data that is available online, or the other companies which do these surveys or provide these data will not be able to provide the localized temperature. So as the crop the field may be very vast, and it might be in the outskirts of the region where the temperature data is provided. So we can use this data. And also if the temperature or the temperature is very high, the plant will lose its moisture more, or if the humidity is very high, the plant will not precipitate that much. So depending on this, we can also predict the moisture requirement or the water requirement of the plant. And the next component is LoRa RA01 model, which is a LoRa model. And this model supports LoRa, TM, FSK, GFSK, all these modulation modes. And this model has a range up to 10 kilometers. So assuming the farmland is very huge, and if the uh, like the node main module is placed in the center of the village, it can have a radius. It can be it can provide connection to the village at the radius of 10 kilometers, which is huge enough for farmland in countries like India. And this is regarding the hardware implementation. Moving on to the software implementation.
Yeah.
In the software implementation with regard to IoT, uh, embedded C to program the microcontroller. And we plan upon using various Alibaba cloud services such as TSDB, Object Storage Service, Link IoT Edge. So TSDB is the time series database, which is especially designed by the Alibaba cloud for storing IoT data, because it has high speed read and write properties. And object storage service is a storage service where you can store any item such as images, video files, anything. So this object storage service, we plan upon using it for storing our images, and retrieve it whenever it is required. And finally, the Link IoT Edge, we plan upon using this service for connecting the devices which are spread around the farm to the internet. I mean, to the server which we want, and use MQTT protocol, and finally send the data from that MQTT broker to the TSDB service database service. So this is all with the IoT part.
All right. Moving on to the impact of the project. The end users of this project would ideally, in the first phase, be small and large scale farmers, agriculturists, horticulture specialists, other personnel dependent on agriculture and horticulture, etc. The user base, the potential user base in India is about 42%, or almost about half the population, if you consider the people relying on agriculture as well. And it's about 30% in the whole world. So as you can see, there's a big user base, potential user base, and there's a good market for our product. And now this success of this project could also pave the way of expansion into other industries, or to open up a new market as a whole. And the effect of this product on the local community is huge. First thing is, it increases the yield in places where water is scarce, and it improves the food security, and it helps use water sustainably along with other resources. And it would all the usage of resources would be very much planned. And the second benefit is, it reduces the expenses and the probability of incurring losses during the production of the crop, as everything is closely monitored, more than what it's current in the current system. The third benefit is, it increases uh, the food security to help reach the demand in the future. So as Kavin has talked about, the growing food demand and the growing consumer class across the world, growing uh, food security is going to be a major problem in the future, and our product aims to solve that. So this project is also scale agnostic, and it can help people from all walks of life. So it's something that benefits all, is what we are trying to say. So some other impacts, Kavin, you can continue.
Right. So we've already explained as to how the whole process is with phase one, with phase two, with phase three. The idea being that you're not only going to talk about predictive analysis in terms of weather patterns, but you're also talking about feedback loops in terms of soil analysis. So you are providing feedback prior to the agriculture, you are providing feedback during the agriculture, and obviously at the end of the harvest, you can talk about essentially like a report card as to how things have gone, whether the satellite imagery of the region of interest has provided very useful information to the large scale farmer, to the small scale farmer, as to how the weather might look like or how their groundwater is. These sorts of things are going to be taken care of. This is like a project where you're talking about the before, the after, and the in between. So that is why in the second phase as well, we are talking about a situation where we are not only giving information to the farmer, but we are also giving suggestions to the farmer as to what crop they might want. Someone might prefer to grow cotton, but we believe it might be better for sunflower. These are the sort of crop A versus crop B type comparisons and suggestions that we want to give to the farmer, with of course the help of the government or even the help of Alibaba, either through scale upgradation or just expertise in general. And finally, in the final phase, as we said, this is not simply an issue regarding food security or water scarcity. We are talking about revolutionizing the way we look at land, the way we look at water, and the way we look at agriculture as an entire industry altogether. This is going to be useful throughout the industry. As I've said, we're not talking about simply, sunflowers and cotton. We are talking about livestock. We are talking about land surveyal. We are talking about country to country projects in terms of water. These are the kind of things that we want to look into for the larger part of the future, which is why water utilization and water efficiency is the core of our project in this regard. Next slide, Nihal. And of course, when we talk about the financial aspects of it, we are seeing a position where what if we could help lower the carbon and water footprint of the larger farmer? Because with the small scale farmer, their carbon footprint is relatively low to the point where carbon taxation doesn't apply. But what if you can approach corporations that may want to avoid carbon taxation by giving them this technology to optimize their utilization of water and other resources? So with this, you're not only giving them a societal ecological goal to accomplish, but you're also giving them the benefit of finances. They may invest a few thousand so and so rupees or dollars into a certain project, but at the end they are yet to avail the tax benefits that they may recover by not giving as much carbon output as they did prior to this project. So this is something that corporations would definitely be interested in. On top of that, we are talking about governments actually bringing the heart of the farming population to the mainstream, and that is by subsidizing these technologies to assist them in terms of supplementing them with more information or just projecting their yield or how they need to go about their crops. As I've said, in the current system, farmers have to wait about 2 to 3 years for these kind of facilities to be availed. We want to cut it down to season by season so that with every harvest, they're not only prepared for what they'll earn in that season, but what they are expected to earn in the very next season. This is the kind of planning that each and every industry has to go through, and we thought when we start from agriculture, this can be our proof of concept as to how we can not only save money, we can not only save water, but we make people's lives easier. And I think that is something that technology and information and innovation always stands for. And again, we can talk about this all day long, but there are also monetary benefits that are outside of the ecological and financial aspects. We are talking about data collection. In a world where big data is now the key phrase, we are talking about a position where if with the consent of the large or small farmer or the government, we can use this data, we can actually provide this information to banks and the government itself who run crop insurance schemes so that they can identify at what time or what position is it right to either provide a loan to the farmer, a formal loan to the farmer, or to provide insurance based on the performance of their yield. So this is how we are not only making money or a commercial or a monetary benefit from the agricultural sector, but we're talking about a whole policy being generated altogether when it comes to data utilization. In short, this is called smart farming. This is where we are not only applying the Internet of Things as a technology, but we are connecting agriculture with almost every policy sector in the country. And this can be applied for every other region as well. India is not a unique space where only this solution can work. We can save plenty of business, plenty of money, and plenty of water in many countries all across the world, whether it be in China, India, or the United States. And that is why we thought this solution would make sense not only on a small scale but on a large scale. As Nihal said, this is agnostic, and it is also policy agnostic. We can help the corporate sector, we can help the government itself. This is how we thought with this one small linear solution, if we can scale it up from phase 1 to phase 2 to phase 3 by scaling it up not only in terms of technology, because the kind of computing you'd require for these things are very large, and at the same time the finances that may be required to genuinely manufacture all our products on a larger scale to ensure that land surveillance and water surveying goes smoothly would require a lot of support. And that is why we came up with this project that could really solve a lot of issues, but at the same time unite a lot of sectors and possibly countries in the way we view water utilization and the way we view land surveillance.
Yeah. And just to add to that, whatever the financial benefits or the financial aspects of this project, all of that money would, the idea is to use the money from the data or from insurance companies or from banks that can use the data for giving loans based on crop growth patterns. And all of this money will be used to maintain the infrastructure, and indirectly, we will be making it more affordable for everyday farmers to use our services. So, this is indirectly just increasing our social value of the project, and it's going to just help further our goals among this. So, uh, moving on. Um, yeah. So um, this is a declaration of originality that all of the ideas that we have and whatever we have done in this PPT is by our team for the intelligent weather forecast for better life. And wherever the other contributions of other reports, etc., acknowledgements have been made to citations and links, you can check them out. And to know more about our project, you can go through the rest of this PPT, and as well you can contact any of us, any of the team members, to know more about it. And just coming back, uh, this is our team. Myself, Nihal, from IIT. We have Kavin Ramesh from ILM University and Mihir present here from VIT Vellore. Other members include Anish from NIT Warangal, Mohammad Rizwan Khan from IIT Madras, Thirumalai Vasan from IIT Madras, and Yash Renwa from VIT Vellore. And just to give a final conclusion, Kavin,